Good morning, everyone. Thanks again for attending this presentation. It's a pleasure and an honor to have Suzana Nunes with us today, presenting her work, Polymeric Membranes for Efficient and Sustainable Molecular Separation. We met quite recently, pre-COVID, but recently Suzana and started establishing a collaboration that is starting to have some results. Suzana's work is dedicated to development of polymeric membranes with expertise on different aspects of polymer science, including synthesis, functionalization, thermodynamics, and self-assembly, aiming at extending the stability and performance of membranes and to propose sustainable membrane manufacturing methods as flat sheet and hollow fiber applications for chemical industry and water sector. Please, Suzana, the room is yours. No, it's not the floor, it's just the room.
Yeah.
Thank you again for accepting our invitation.
Thank you again. Thank you, Pedro. Thank you very much. Really a pleasure to talk, especially to talk to Aveiro. So you might not believe if I tell, but Aveiro is one of my favorite cities in the world. Really, I always dream to, maybe someday I will live in Aveiro still. I really like it very much. We cannot be together now, person to person, but so I think it's a good start that we collaborate, and I think that will be a good chance to have an overview of what my lab is doing now. So I work with polymeric membranes for many years, for decades now. So in my lab at KAUST is developing membranes for applications that goes from water separation to chemical applications, chemical separations in industry and so on. The focus is material itself. This is the preparation of the membrane, the control of morphology, of pore formation and so on. And we have quite broad of examples on how polymeric membranes can be prepared in different ways and applied. Before starting to talk really on the topic, I don't know how many of you heard about KAUST. I should have brought some slides about KAUST, but KAUST is international university in the Middle East. It's on the coast of Saudi Arabia. It is like we are like a campus, a city apart from, and directly on the seaside. And it's a place. It's now a little bit more than 10 years, the inauguration of the university, completely international and for PhD and master students. Research is a focus, engineering, science, and so on. And I think has been a really very pleasant place to work, very productive, very competitive, and I think gave us a chance to proceed a lot on membrane development. If you have questions at the end, I can be glad to answer on KAUST and other topics. So this year, you might know. So each year there is the S20, or so the science part of the G20 meets in some place. This year was in Saudi Arabia. At least that was the plan, to meet here personally all the scientists from the Academy of Science and meet to discuss what would be the most important topics at this moment, where we need to invest time and research. Of course, this year was a little bit special, but there was a very nice discussion. And one of the main topics was circular economy, the need to propose solutions for the issues in environment, to improve environments, and so the way that we have today. And circular economy can be very broad, but in part what is relevant for my work, and I guess for many of you, is how like chemical process, how water use and reuse affect the environment, affect our lives, and how can we improve that. You see this diagram here. Of course, water is a big issue, not only in the Middle East, but here is a very special issue because it's a scarcity. So, one way is constantly desalinate from seawater but it is also needed to recycle that. So it's also the desalination itself costs energy, and really we in parts of Saudi Arabia, but also I know that in parts of Europe, like in Spain, so there is a scarcity of water, and it's not always the seasides immediately available. So this is one part of the recycling, but we know that any from transit, from traffic activity, in industrial activity, so we produce CO2, and is a consumption of energy and use of fuels, of CO2, of greenhouse emission, and warming and climate change and so on. And there's a lot of discussion if it will be or how and we can solve this issue, or at least minimize. How can we capture CO2 and maybe store or reuse? Store is also a problem, but I don't know if this is the most the best way to go through it, or we could also act before that. So how can we minimize the production of CO2? And I believe that membrane technologies can play a role on that. So we can have more efficient separations. We can have more clean environments in the industry, having like zero discharge in industry. We can have also membrane plays a role also in the energy, in renewable energy itself. Fuel cell, for many years I worked with fuel cell in Germany before joining KAUST. Battery is a very important issue. So here, for you, probably you know that already if you are more from chemical engineering, but you know that really 10 to 15% of the energy used in the world, consumed, is for chemical separation. And from this chemical separation, 80% is still thermal separation, like distillation, great part, evaporation, dry. So this is really one source of CO2 that is not so visible for the normal person on the streets and so on. And again, so it's we could go on in the same way, and we high energy demanding separation and so on, and we continue to produce CO2, continue to use fossil fuel, and we'll have a problem that will be growing and growing each day. Or we can be proactive, and we can use renewable energy, which I know it's an important topic in many countries in Europe already, but start to be a discussion in all countries, including Saudi Arabia, which is basically a fossil fuel country, strong economically dependent on that. Still, there are really many discussions in diversifying that. Okay, this using renewables already reduce CO2, but we could, as I mentioned, be more proactive and substitute part of the separation process in the industry by low energy process, which one of them could be, or kind of for a series of them could be membrane technology involved. This is, I think it's a huge opportunity for membranes. In a few, last year, we met with a group of membrane scientists in Austria and discussed what are the top topics that are really the most needed topics in membrane technology. And following what my previous slide said, I think if we want to substitute chemical process, a big problem until recently was the stability of membranes, because membrane is very good for water, has been there for 4 or 5 decades, really optimized and using desalination in really large scale. reverse osmosis, as we apply pressure and filtering the seawater. But for chemical separations, many times you need a membrane that will be much more stable because you use solvent, you use sometimes high temperature. So the need for membranes with a much better stability is a hot topic. Is something that we really need in this field. Of course, in any membrane, we need a high selectivity. We want to preferentially to work with high permeance, and we have to be free of defects and so on. Then a field that is growing much more, so reverse osmosis is quite established. Nanofiltration is a field that is growing more and more. Nanofiltration will be very useful when we think in separating molecules which have a similar size. So, you know, we have excellent membranes for reverse osmosis that reject salts, very small molecules, but they reject everything. So if we want to separate in the pharmaceutical industry two substances that differ very minor in size, or they differ in shape, or, you know, if you are related to chemistry, you know that chirality is can have consequences which are really very sometimes unpredictable. You know, classical examples of medicines which were given to pregnant women in the end of 50s, beginning of 60s, that caused deformation in birth and so this. And this was because of the chirality. If you change the chirality, you have a good medicine. If you have the wrong chirality, you produce really health issues that are difficult, really impossible to solve. So all these are points that we have to think when we are working with membrane. So membrane, polymeric membranes, they are good way to produce. They are very easy to process. Let's say easy if you know how to do it. And there are basically two main configurations. One is like a flat sheet, like a filter, that I think more common. Keep in mind that we can have just a pure porous materials or asymmetrically porous, or we can usually have a coating on the surface of this porous substrate, or we can prepare it as a hollow fiber, so like a really a noodle machine where you have but with a hollow in the middle. So you have a porous wall, and you can circulate the feed outside or inside the fiber, and you, by applying pressure or vacuum, you can separate also, and you have a very high ratio of area to the same volume. So you have modules of membrane which with a very compact, very small volume, but that you can really have a very surface area, and of course is very effective. So in both cases here, the way it works is a solution process. Usually you cast on a textile, on a non-oven, and immerse in water, and you have the coagulation of a film. The process, I think, I don't have much time to go into detail, but it's the way the pores are formed. And the hollow fiber is more or less the same. So you extrude a solution of a polymeric solution, and then this is immersed in this incipient solution that's being phase separated, and you have the formation of very porous materials. So the key point here in the hollow fiber is a spinneret, so like the head of an extruder. So we have been working in different aspects of everything that I mentioned. One is to have membranes with higher temperature and solvent stability. And we know that there are many polymers which are not regularly used for membrane that are very stable. So they are stable up to 500 degrees. So there are few of them. There are not many, but there are few of them that can be used. But to prepare membrane, you also, as you saw in my previous slides, you need a good solubility. You have to have a solution to process, and then it's a little bit of conflict, because you need a solution, and then you prepare the membrane, and if you use for a chemical purpose, you don't want the membrane to be dissolved or to be degraded in the presence of solvent. So you have to play with this stability against solvent and temperature, but also be able to have a good solution for the membrane preparation. Some of the polymers that are very stable, that you can see here, stable, close to, in terms of temperature degradation, they are close to 500. Of course, you have to think also that some of them, they are stable chemically, but they will become soft or melt in temperatures that far below the 500. So I mean, there are a few of them that are good for that. It's polyoxine indole that we worked more recently, polytriazole, which actually is much higher than 300, what I have here. And okay, but this is a really very good start. And we have membranes prepared in all of them here: polyether ketone, polytriazole, PBI, and polyethylene terephthalate. So one that I mentioned as very, very stable was the topic of a PhD thesis of Bruno Polido, who just finished the PhD. He's now working in Neom, which Neom is a futuristic city that's being built in Saudi Arabia, in the north of Saudi Arabia, in the border with Jordan. So it should be completely environmentally friendly, high technology, artificial intelligence, robotics, everything that you imagine. And I think it's a very nice place to be at this moment. But he produced polymers which have this structure here. They are soluble because you see the structure is not very easy to pack, the chemical structure. So it's you have a bulky group here that allows you a high solubility, but at the same time it's chemically very stable. And also, once you prepare the membrane, we can easily cross-link. So in his case, he substitutes this hydrogen here of the nitrogen and had a triple bond, which then becomes very reactive. Then he tried different process of cross-linking. I think I don't have much time in going detail, but from thermal cross-linking to reaction with like click chemistry or photo cross-linking, a lot of different strategies. This is another polymer that we worked a lot, which is polytriazole, which again very stable. And I think this is interesting for you because you have a very strong group in ionic liquids in Aveiro. And what we have been observed is we are trying to substitute the like classical solvents like NMP, DMF. First, the motivation is that these are the NMP and the DMF, and so they are considered toxic solvents. So they, if you see in the classification, especially in Europe, so they are not completely banned, but they are very controlled. So if you have they have to really done and has a lot of rules to time of exposure. And the tendency is probably to be away of this classical solvents. One moment here. I hope that my connection is okay. Continue here. Okay. Then the motivation initially was to substitute those solvents by ionic liquids. Also because with ionic liquid we can dissolve some other polymers which very hard to dissolve, like cellulose. But the polytriazole could be dissolved with this amine DEP, this one here. And the nice thing, the nice consequence of that is that it's not only, this is the cross section of the membrane. So here's the surface looking at the membrane from the top here, but then the cross section, we fracture the film and we are looking from the side. And we see that with the regular NMP is a very big cavities. So this on the top is selective, but this doesn't bring the membrane a very high stability against pressure. So, and if we work with ionic liquid, we have a very porous structure, but much more like sponge-like and more stable. So this was, and we observed that for many polymers that by now we succeed to prepare membranes based on polymers and ionic liquids. And then I showed these plots. I will go just fast through them. So what I mentioned is we use this kind of di-epoxy to cross-link the polytriazole. And with that, we have a quite stable membrane, and we control the rejection if we prepare if we test also in different temperatures. So we could test up to 100 degrees with a DMF, which is quite a strict condition for filtering. Then this was the other polymer that I mentioned. This is a commercial polymer. So I think the conclusions are more or less the same that we saw before with the ionic liquid. We have a very spongy-like structure, cross-section, and with the DMF is a more open structure. Then I'll start to talk about the cellulose, and I would just go back to this bottom here, which is something that usually you don't care much about. So I think usually we use a regular SEM for, but this is a membrane which swells a lot in water, and we saw a difference in separation capabilities. But when we were looking at dry membrane in the SEM, we didn't see much difference. So what we did is we brought the membrane to a cryo microscope, cryo SEM, and we can see then the porosity with the frozen membrane, like in the state that would be in water. Good. I go to this part here. This is another approach that we use, which is polyethylene terephthalate. Polyethylene terephthalate is a polymer that is basically the polymer that we have in plastic bottles. So used in very large scale, hopefully decreasing now, or I don't know if it will be completely banned, but at least if it's not banned, we could, is a cheap source of polymer, and is to find ways to recycle it, to use in a valuable way. So we were investing in preparing membranes from this polymer. It's also, again, difficult to dissolve, but we could dissolve in hexafluoroisopropanol or trifluoroacetic acid. Trifluoroacetic acid is more aggressive solvent. You don't really want much to use, but hexafluoropropanol is a quite mild one, and could prepare also membranes, very porous one, very good ones that we can use as a support or not. Good. Then I move to just to show some of the coatings that most of them prepare if you just prepare by this coagulation. So they are too porous to be selective. And what we normally do is to coat this asymmetric porous materials or membranes with another very thin coating. And a classical way to do that is interfacial polymerization. So interfacial polymerization, you do the following. You have a water, aqua solution with one monomer, and then you have an organic, an apolar solvent, and a second monomer which are dissolved, and the two phases do not mix. The only contact between the monomers is the interface between the water and the organic solvent. So when they get together, they react and they form a thin film of polymer. And this is the principle of many of the members. So I think the principle of one of the most successful membrane in desalination, which is the FT30. So at the end, the polymer is a polyamide polymer that is formed at the end. You see this is a coat, and this is colored here because the thin film is so thin that it's in the range of the wavelength of light. So it's it's just because of interaction with light that you have the color. So, but we get even thinner than that. So it's and you see here the cross section of a membrane with already with a top layer of a very dense film, very selective one. They are the classical one is done with the small molecules which are the trimethyl chloride is an acid chloride, this molecule here, and then a simple only the benzene and diamine. This is the classical, the most classical monomers for interfacial polymerization in membrane. But in this one, what we use is a cyclodextrin, which is functionalized with amino groups. The cyclodextrin then will give, because it's a macrocyclose, it's a preformed, so will give us separation for molecules that will fit exactly in this cavity here of the cyclodextrin. So then at the end, when we have this polymerization, we have a lot of these cyclodextrins cross-linked all together, like this one here. So and we could separate then molecules that have specifically the size of this internal cavity of the cyclodextrin. So with that, we have very thin selective layer. That means the resistance to flow, to transport of liquid is very low because it's a very thin dense layer. And because of the size very uniform of the cyclodextrin that will form the pores really of the membrane, we have a very selective one. And the separation here, we say when we have a more or less 90% of rejection of a solute, then we say this is the cutoff, so the molecular weight cutoff. So this membrane is around 400, 450 grams per mole. And better than that, the membrane is quite stable in solvent because it's everything cross-linked. And we can also separate by shape. So we have here two dyes which are very similar in size, but one is more linear, so more elongated, and the other is more bulky one. So we could separate also by shape. So it's this very strict separation. And the good thing is also that this is this is developed in our lab. This is a really new material. So, but use a technology that could be easily upscaled in machines, because the principle of the technology is the same principle that is used for large-scale production of membranes interfacial polymerization. So it would be just to adapt to the material and so on. And this interfacial polymerization has some environmental drawbacks also, because we use the apolar solvents very frequently, hexane, and so in this work here, what we did is we substitute, instead of using the organic solvent, like more or less toxic, we succeed to substitute by oleic acid. So and this was possible to prepare interfacial polymerization membranes in a much greener way than usual. Well, let me see. I know my time run. So I will show this one is also interfacial polymerization. It's also prepared more or less in the same way that I said, with the organic and the aqueous phase. But this is a paper that we published this year in Science Advance. The main author, Jiantao Liu. Jiantao wanted to have a membrane that is that will be sensitive to light. So that means to have a separation that could be tuned by light. So he prepared and he used this polymerization, what is actually we can call covalent organic network. He used building blocks that have this azo group here. This azo group is known to be sensitive to light in the sense that if the right wave length of light is applied, so this molecule here will bend like that. Then if the idea is, if you have in this mesh of this network here, if you have building blocks of the azo group, so you could bend open and close like an origami, like that. And he combined with a cyclic molecule that will really, let's say, alleviate this stress when you bend the other building block. So if I would have all these azo groups or so, if I have a fixed membrane, when they will bend, it will contract all together. But combining the two molecules, I can just open like it's demonstrated here. It's like only the pore is open and close. And with that, I can separate molecules of different size just by irradiating with light. So I think this was a really very clever idea of Jiantao. And this is how it looks like. So you have to start to prepare the film. It's a very bright color. And at the end, you have, like the one that I showed before, just 50 nanometers of selective layer, which is really very thin, very high flux, very high permeance, and is still very selective. And again, of course, you have some time that you irradiate. It's not seconds. It's like a minute or so, and then you want also to have it cyclic, so that if you irradiate with another wavelength, the molecule that the segment was bent, it will become stretched and return to the original size of the pores. Good. Let me see how much time we got. So maybe I should just one on the example. This one is another kind of coating that we have with the graphene oxide. But I think because I have a short time, I will go to this one. I will not. We have a very nice collaboration with Pedro's group, with Liliana and Pedro, and this one is not the work. Our work is about to be published. I ask you to be really to check the ACS Sustainable Chemistry and Engineering in the next days, probably next week. It will be published. What I will show here is also for the same application that we test, which is a membrane for dehumidification, but is not our work. Our work, I think, we cannot show now, but in a week you will see. So the idea here is we are working with the group that is more effective air conditioning, and you know that not only here in Saudi Arabia but in other countries you have a very high humidity level in my campus, so it's very humid. So during the cooling system, you need to control the humidity also. You can have a lot of condensation. So then we want to apply dehumidification module, membrane module, to take the water out and be part, so that the whole cooling system will take place without this high humidification. And the way that is being done is that, again, for hollow fiber, you see this is a cross-section of a hollow fiber, very porous, and we coat with a dense layer of a polymeric material. And in this case here is a block of polymer named Nexa, which is a pentablock. So you see has segments of different blocks. The hydrophilic one is the sulfonated one in the middle here. In the case of work with Pedro, I can say we use the capsules with the ionic liquid that he is producing, then we integrate in a polymer that is a more common polymer for a very nice, very effective approach and very successful. Here in the case of Nexa, Nexa is a block of polymer. That means a block of polymer is able to form a very complex structure because they have one block, or in this case 5 blocks, some which are very hydrophobic and another which is very hydrophilic, the sulfonic one. They don't mix it with each other. So if you look in the microscope, this is an AFM microscopy. You see that very nice morphologies here. So we want to have, preferentially, to be effective, from one side of the coating to the other, I need to have channels. So, and we saw that we coat with the Nexa just by immediately coating, and you look at the surface of this material, we see a lot of nodules. What is the question? Is this nodules or cylinders going from one side of the other? Then we start to anneal that with a solvent that is a good solvent for this polymer. And after 2 days of annealing, we see that this structure is changing. It's becoming more like lamella or cylinders. So 8 days, we have a quite nice structure here. And we can see that so if we cut the hollow fiber after the coating, in 1 day we have the nodules here. The cross section is also more or less nodular. If you anneal that, we have a more like channel forming. So this I will not go in detail. This is a kind of measurements that we have. So with the hollow fiber cylinder, it's the same kind of modules that we use for other applications like hemodialysis, use the same kind of modules. And good. And after the coating, we see that the water vapor permeance, depending on how long is the time of this is not the time of annealing, it's the time of coating. So if we immerse in the solution with the polymer, depending on that, we control the permeance. We can have very high values, and we can have some selectivity on water and air, or water and nitrogen also. I will not. I think I have to stop now for having questions for you. Maybe another time I can talk about isoporosity, which is another part of my work. But this is really not enough time. So with that, I want to thank you for having time to watch and discuss with me. And this is a more or less recent picture of my group. You can see more about the group in this quite diverse group. And this is a picture of KAUST. So if you have the chance, hopefully next year we'll be in a much better situation and we start to travel again. And I hope to host some of you here. So this is we're really directly on the seaside, and I think it's a nice place to live. And I'll be glad to have questions from you.
Thank you, Suzana, for this very, very interesting talk and show us the wide applications for these kind of membranes. I believe that some of these applications are focus of our group. I believe that some people will have some questions, so feel free to ask. No one? So I have one curiosity. It's about using ionic liquids. You are using ionic liquids on the synthesis, on the preparation of the membrane. Mm-hmm. What about supporting ionic liquids in the membrane?
Yeah, this is an important strategy and has been explored by. So there's a group of Richard Nobel in Colorado. He used for gas separation. It's a very effective method because you can really, especially for CO2, and so you can have a very high selectivity. You know, he worked for a while with that. I think he still works. Of course, you have to control with liquid membranes, what we call liquid membranes, that you fill the pores with the ionic liquid. You have to control also the stability of it, so you cannot apply much pressure. So that there are strategies to polymerize also the ionic liquid to have the same, more or less the same efficiency. I have one paper where we relatively polymerize groups which are present in ionic liquid before joining KAUST. It's also an interesting strategy, but okay, that's a completely different approach.
Okay. So, any question? So yeah. I have someone asking to feel free.
Yes, go on.
Go on, Nicholas. You are muted still.
Shit. Hello, good morning. Thank you very much for your presentation. I was wondering, especially on the membranes that you modify the surface with cyclodextrins or these circular amine compounds. Mm-hmm. These are often good ligands for like a lot of salts that you find in waters, like sodium, lithium, and so on. Do you see? Well, first, do you see these membranes being applied for metal separation? And two, do you see an increase in fouling if you have a high concentration of these salts on that thin surface?
Mm-hmm. Yeah, I think it is. It could be useful for this kind of separation too. So I think in some macrocycles with ethylene oxide, so they are mm-hmm. quite. Have been explored. I think this is still a lot to do in this direction, but they can really have exactly the size of some specific ions. Yeah, fouling is always a problem when we work with water, and if you have depending on the quality of the feed, no. So yeah, I think you probably, if you want to have you might have some pre-treatment to apply for that before, I think. So have fouling is another issue. I think I can talk also hours about how to mitigate fouling.
Oh, okay. Thank you very much.
You're welcome.
Thank you, Nick. Any more questions? No. So if there is no more questions, I need to thank you again for accepting our invitation. This is very interesting talk. We'll keep in touch. Hopefully we can continue with our collaboration. It's very interesting. Hopefully in better conditions on the world next year, but nonetheless we'll still work together. Thank you very much again for your presentation.
No, thank you. Thank you. It has been a pleasure to talk with you too. Bye.
Thank you.